Welcome, we're going to be doing Physics 123, lab number 7, Diffraction Grating. For this lab, we have the following laser. This is a helium neon laser. It's red and has a wavelength of 633 nanometers. That's what all helium neon lasers have as their wavelength, so 633 nanometers. You might want to jot that down. We're going through a diffraction grating. We don't know what the spacing is like on this grating, but it's just a bunch of vertical lines that the light is going through. And as we can see, once the light goes through this grating, it's actually diffracting. And we can see, if we turn off the lights, we can see on the other end of the wall an interference pattern that is formed. So we have intensity peaks, and then where there's constructive interference, and then places with no light where there's destructive interference. And so what we'll do is, since we can't record electronically the light over there, what we're going to do is have this CCD camera, the same CCD camera we used in the telescope lab. We're going to go ahead and place that there and record that diffraction pattern on the chip of the camera, and then we can go ahead and send that data to you, just like we did with the telescope lab. So that's the equipment here. For part A, you're going to need to draw a diagram kind of showing what's going on here with two rays coming out of neighboring diffraction slits that end up in an intensity peak. So like we saw, we had a peak here in the center, and then, further peaks out. The spacing should be consistent with each of these peaks. And if we just look at one of them, say the m=1 case, the first order case, we have light coming out of the diffraction grating, and it's interfering here. Okay. Now we could measure, and we are going to measure this and this, and so we can get this angle. And the trick is we want to be able to relate that angle somehow to what's happening on the individual grating. So we could think about this as being extended, right? But if we just take any 2 points on the grating, okay, we have light coming from here and light coming from here. Now they're going to converge to a point at the intensity peak, but this is really far. So we're just zoomed in right next to the grating. We can treat them as approximately being parallel. And so what we see is that the light from this one has an extra path length here, okay? And this path length is going to cause it to be phase shifted, is what we call, from the other light. And then when this path length equals 2 pi, it's going to be constructively interfering because they're kind of shifted over but right on top of each other. You should have talked about this in class, so hopefully this isn't new. But this is a good starting point for your diagram. So I would draw one far out showing the diffraction pattern, what's happening, and one zoomed into the actual grating and what's happening with the path length here. And so go ahead and draw these out and make sure to label all your distances and angles and what angles are the same between them, and that's going to help you a lot in part A. So, okay, for part B here, we have gone ahead and placed the CCD camera in line with the, right after the diffraction grating. As we can see, this is a live image of the feed. We're kind of washed out. The CCD camera can only detect light that's so intense, and it's saturating. That's what we call it. It's maxing out the screen. So what I have here, I have a couple filters here, and they're just kind of going to lower the intensity of the light. And if I place them in between, we can now see the diffraction pattern appearing. And it turns out that center peak is still saturated. So what we're going to end up doing is including even some more filters on top of that to get it so that we have no saturation at all. And so that's kind of our final image. Now you can see that if I take some of them out, it's just the diffraction pattern that we see before, but a little bit dimmer. And so it'll work for our purposes. Now what we need to do here is record all the relevant data before we actually capture the image. And so what we need to note is it doesn't matter how far back the laser is from the diffraction grating, but what does matter is the spacing between the two. And so if we come in here, we can make our measurements. There's a little ruler. This is in centimeters. There's a centimeter ruler in there. It's a little bit dark. But that says, that's the 59 right there. So if we come in straight, you can make this measurement yourself. The center line there is where the center line on this holder lines up approximately to where the diffraction grating is, okay? Now there's going to be some uncertainty with this measurement. On top of the uncertainty, just from not knowing what this may be in here, we're going to have uncertainty because the diffraction grating may not actually be where that line is. There could be a couple millimeters that we want to add, just since the diffraction grating is not exactly in the center. Same thing with the camera here. We can say the chip's roughly in the center of the camera, but we could be off by 3 to 4 centimeters, or sorry, 3 to 4 millimeters. So include that in your uncertainty as you make this measurement here for the center of the camera or screen. Okay, so we have those measurements. The next thing that we're going to want to do before we actually get the camera measurement is figure out what the distance. We can see on the chip, right, there's the diffraction pattern. We want to be able to relate the pixels on the chip to actual real life distances on this on it. And so on the telescope lab, we did a similar thing, but I just kind of did it for you. In this lab, we're going to have you do it. And so this is the spec sheet of this particular camera we're using. Okay, and so this is across, the pixels across is 1280, and that's what we mainly care about. So 1280 across, and then that's 6.656 millimeters. And each pixel is 5.2 micrometers squared. So that's 5.2 on each side. Okay, and so make sure to jot those down. You're going to need them in a second. The other thing that we want to do is measure the width across of the diffraction grating. Okay, I've got my calipers here, and I'm measuring across the width, and that is 34.91. So about 35 millimeters for the width of the diffraction grating. And those are all the measurements you're going to need for the lab. Let's go ahead and collect the data. All right, I've gone ahead and put the filters back in here. So they're reducing the intensity of the light, and we can see the diffraction pattern is being captured on the screen. Now what we can go and do is hit save here and save this image, or capture this image. All right, we have pulled up the picture that we took here into ImageJ, the same program we used for the telescope lab. And in that program, we just did a single line out. So I just took a line across where we were interested in, and it plotted the intensity and the pixel value. Okay. This time, since if we look at the picture closely, it's not the cleanest picture, and a lot of that's because we had to put in the filters to reduce the intensity. There are some other effects, some scattering and stuff that, and to be honest, our laser isn't the most coherent source, and so this isn't a perfect picture. And so in order to try to do that, what we're doing is we did a box out, and this is taking each horizontal pixel and then averaging the intensity across each pixel up and down in this box. And so we still get a plot similar to what we'd expect. This is intensity. Again, gray values corresponds to intensity. So we see the center peak was the brightest, and then the next ones are a little bit dimmer, and then it kind of fades off. This isn't, if we had a perfect laser and a perfect camera, these would be nice and uniform. We can see some what we call noise here, or kind of inconsistencies in the data, and that's okay. We can still work with this and get the spacing between each peak is what we're mainly interested in. And so what I'm going to do is I'm going to go ahead and save this data, and I'm just going to save it like the data that we used before, a CSV file, lab 7 diffraction grating data. And so this is the exact data we're going to be sending you for you to interpret. Again, like I said, this is in pixels. It's not in distance, so you're going to need to do that conversion yourself. And there are some resources on the student sheet to help you with that. Don't be afraid to reach out if you did have any other questions. But that's all the data that you're going to need for this lab. Good luck with filling the rest of it out, and thanks for watching.